Hello. Yes, I'm worried about you guys. Where are you? I haven't seen any of your work, and I've seen Charlie's, so thank you for that. Haven't seen anyone else, so I need to know where do you guys up to. So hopefully, you should finish one and then two, and there would be questions attached to each clip. I need you to finish them as well as the workbook. By the time I come back, I don't want to be like 3 weeks behind, and I need to go through all again. I'm not going to go through any more video clip with you, like all those concepts. I'm going to like force you to sit down next to you, and do it, and just try to do it with find some time to yourself. Yes. So basically, you're going to do it anyway. If you can, remind some people that they're in the chemistry class and they haven't done those videos, please remind them. I will trace them up, and the workbook as well. Yes, there's no leeway. You have to go through it. It will be, and no matter it's boring or what you want, those basic concepts that you need to understand. For remember last class, I kind of touch on the concept called relative atomic mass. So RAM and the formula. And the formula related to it. And hopefully you will be able to tell me about what RAM stands for. RAM stands for the average of all the isotopes based on its abundances. Right? I'll say it one more time. What is relative atomic mass? Relative atomic mass is the average mass of all the isotopes based on its abundances. Right? So abundances means that some elements will have different different types of isotopes, and each isotope, some of them naturally would have more than the others. So when you try to say abundances, you need to know the behind meaning about it. So RAM, relative atomic mass, you have to find one thing first. We call them isotopic mass, which is the mass of isotopes. Carbon-12 and carbon-13. You look at the mass number at the top, most of the time is good enough. But some question may be very tedious and giving you like 5 decimal points or 6 decimal points. You may find a little bit difference between each other, like variations. But this is very tedious way, and I don't think in year 11 we need to understand, or we need to like be kind of tortured by those very like tiny differences. So if you see some question basically going through that, it's okay. You can go through them, but I don't really, personally, I don't think it's necessary, because like the percentage is good enough. If you have a good percentage, the relative isotopic mass will not be bothered too much. Yes, so today what I would like to do is try to continue with this topic, and then giving you something in details about a machine that's helping you to find out relative atomic mass. We call it mass spectrometer. Spectrometer. I nearly can't spell. SPECT. S-P-E-C-T. Spectrometer. And generally we call them MS. Mass spectrometer, MS, is the machine that we try to find out the relative abundances as well as the isotopic mass that we need for the RAM. So here I researched that to find. I always like to use a very simple diagram like this one. Sometimes there's lots of other books or whatever, they use very complicated one. I think they are useless. And all you need to know about mass spectrometer is a long tube, and these tubes with a band at the end and different parts. And there's no need for you to draw the diagram, but something that you need to do is to be able to identify certain parts of it. There's not many parts. Generally, the first part is right here. Right? is the way that you do injections. So number one is always the injection point or injection pot. It's a ring with a very fine tubes attachment into it. That's it. You just squeeze your elements in it and everything will be fine. But the one that right after is very, very important. Every single part I try to explain to you will be important in terms of the functions, and each of the part would have all different tiny devices or tiny gears in there to make it possible. The number two, in general, we call them vaporization chamber. Some people call atomizations. Vaporizations. So you know that when you try to vaporize water, you change liquid water into gas steam. So vaporization means that you change those injections into vapor. Sometimes vaporization has another term called atomization. Atomization basically means that when you try to change something liquid into gas, the gas is turned into gas particle further away from each other. So it's more like individuals. And atomization basically try to pull them apart as far as possible, like atoms, like individual atoms itself. So vaporization, atomization. It's a very important process. Most of the time, I would say I'll highlight them in red because vaporization requires heat. There's a lot of heat. Like you may have a flame, like very strong or high temperature flame in it to just vaporize it in a very short time. Then once you turn them into a vapor, each one of them would be very, very light. When you have them very light and individuals, then it comes down to the number three. Number three is in this part, and number three is called ionization chamber. Ionization chamber basically is electron guns. So all the electrons on one side is ready, and you basically try to shoot them out. And all the electrons shoot them out as the gaseous particles come through here. Most of them, 99.99 or whatever, most of them would get knocked by the electrons. But electrons are so tiny, they won't be able to knock them off or knock them backward or hit them. The only thing that the electrons do would be knock down the outer shell electrons, or what we call the valence electrons. If you take away the electrons, let's say sodium, you take away the electrons outside, it becomes ions. So all the elements come into it, or all the isotopes come into it, would get knocked down 1 or 2 electrons, and most of them bear 1 positive charge. When the electrons being knocked down, and all of the particles become charged. Ionization chamber, also charging chamber. You just make it into a charge. Once you get them into a charge, you move right very close to it. It would be a what we call acceleration point. Acceleration. What color do I want? Yep, that one. Number 4 here. We call them accelerations. In terms of what happens when you accelerate, when ion accelerate, it basically going very fast. When you go fast, going forward, because they're going so fast, slightly change would make them into a big turn. So anything that going very fast, like when you're driving a racing car, slightly turn on your steering wheel, make a big turn because it's so quickly. So the reason that we accelerate because they are very light. So everything inside the basic ionization chamber, they are very light in mass. So if you want them to make a turn, you need to make it into a very, very fast. What is the technique that we try to do to make it into a very fast, to accelerate them? We know that they are bare positive charge after ionization chamber. All the gaseous particle will attract to the negative charge at the end on the other side here, not negative charge, not positive. So we've got the negative charge fully charged on this side, and a positive would get attracts towards it, right? So once they got acceleration to the point is fast enough, it comes down to the last part highlighted in yellow. So what is this particular curve part, and what does it made of? The highlighted yellow one, they are strong magnet. It provides a very strong magnetic field. When you do a magnet towards a charged particles, because they will create magnetic field will affect the path of it, and each one of them would turn slightly because of the magnetic field. So just like two magnets running towards each other, and then they will get repelled or attracts. So once they've got that interactions, and they applied a deflection on it, and all the charged molecules get deflected, or the path get distorted. Instead of going straight, it get bended. And the strong magnet there help them to get bent. Now the last part is right there at the hole there. It's basically called collections. And this is just a collection point that holding, if you've got the right path or twist the right way for the charged molecule, you end up heating the plate, and this plate collect all the charge and change those charge into a signal, and those signal will pass it on to number 7 here. We call them display, and the display has a name called spectrums. Where am I now? Yep, there you are. Highlight this for you. It's called spectrum, and spectrum is a collection of all the little straight line, or all the signals from the collection point. So you'll see, like, how come there's so many lines here? Deflection can be used for the deflections. The deflection is run into a scan. So when you do a scan, you start from a strong magnetic field, then you twist, getting stronger and stronger and stronger. When you twist along that, the graph would continue, like from the first time, then the first second you may collect 100 of them, then the second, once you make it stronger, then the next second you collect maybe another 50. So along the time, because the deflection change, then you will be able to collect different types of ions in there. And one important fact about this collection is compare the purple one, the blue one, and the right one. This is basically explain to you what's going on. The green one is too light, so for the magnetic field, the magnetic field there, the green one is too light, so that it bends too much and not being able to hit the collection point. The purple is too heavy, that means it's not bending enough. So instead of hitting the plate, it just hit the wall, so going not enough, not bending enough. The only one that will be able to land on it would be the right weight. So the right side, the one that with the right mass. So because of the magnetic field, and we know the magnetic field is directly related to the mass of the ions inside the mass spectrometer, then we can understand, we can write this XSS, instead of time, we write it into a mass per charge. Mass per charge. At as the X values. Then you will understand one more thing is, if you collection point, the one that with more ions in it, if that ions, the blue one, compare those three, the purple, the green, and the blue. The purple is 10%, the blue is 50%, and then the green is 40%. And you will collect more signals when you set the magnet or deflection field at that point. So if you set that deflection as like whatever values come up, and you collect the blue, and the blue has 50%, then you will collect more signal than the other two. Then once you flip it, then the blue turn into like, there's too much for blue, it turn into purple, the green turn into follow the blue path and goes to the collection point, and even it land into it, there's only 40% signal, so the signal there would be a bit less. We call them peak area in mass spectrums. When the amount of ions collect in the collection point. So after all this, we have the injection, vaporization, ionization, deflection, and then down to the collections. Everything's been done. The only thing that we care in year 11 is the graph. So here is the graph. Most of the time, you will be either a straight line, like the one above here, or a curve. So no matter which way you do, it basically means the same thing. Let's say, what happened to this particular graph? I collect a pure magnesium into an injecting point. Then I melt it, I increase, basically I melt it and then evaporate it, turn them into ions. And once I turn them into ions, each of the magnesium will get very fast to get ionized by the electron guns, by shooting them into the chamber. Then once they become charged, they will be able to accelerate by the opposite charge on the opposite side in the acceleration chamber. Once they are fast enough, they will reach the deflection, they reach the magnetic field. The one that at the right mass will follow the path directly land on the collection pot. And when it lands on the collection pot, it creates a signal. If there's many ions follow that blue path, then your signal will be bigger. And the signal is directly related to what we call abundances. The relative abundances would be able to measure by mass spectrometer, right? Two things that we need to care for this one: X assets and Y. Using those two X and Y, we can do relative atomic mass just by this graph. Nothing else. You don't need to look for words. If you hate reading anything, just looking at a graph. And this is what scientists do. Relative atomic mass is equals to the average of all the isotopes based on the abundances. What is the isotopic mass? We've got 24, 25, and 26, right? And you imagine, or you try to take the average, but you take the average, it's not that divided by 3. If you divide it by 3, means that each one of them would be 33.3%. right? So basically, if you just do 1/3 of this, 1/3 of this, and 1/3 of this, and you're taking the average and you plus them 3 together. However, instead of saying they're exactly the same, 24, 25, 26 have different relative abundances. One is 79, one is 10, one is 11. 24 is 79%. I write 79% here. Then I have 10% of 25, and I have 11% of 26. As is all percentage and relative atomic mass is AMU, atomic mass unit, I need to divide it by 100 to go back to the right decimal point. Now, let's try to do this. So if I try to write this one down, just give me a second. Move across. 24 times up by 79 plus open bracket, which is 25 times up by 10, close it, and then plus it again, 26 times up by 11. Oh, sorry. I've got 2,432, then I divide it by 100. I've got 24.32 AMU. And most of the time in chemistry, we just need 3 significant figures. Therefore, 24.3 AMU would be good enough as our answer. Right? So that is how we do relative atomic mass based on the graph that we have here. Always on the graph, 24.3, straight away, right? So hopefully you will have no problems related to it. Yes, there will be other questions related to that too. So let's say the other way around. If I want to find out percentage, so let's say I have 79%, I do 79%, and then I have, what do we call? What do we do? What do I do? What do I do? At 79%, then I would say that the other two, would be 21% on the other two. Let's say I don't really know which one would contribute to the percentage, but I do know one thing: 24.3 is the relative atomic mass. And I know that the magnesium 25, magnesium 26, and magnesium 27 would be able to find in 24, 25, and 26. 24, 25, and 26 would be able to find in there. And my question is like, yeah, what would be the percentage for magnesium 25 and magnesium 26? Is it a way that we find out without, like, when the relative atomic mass is given? Is it possible to do that? It should be, right? Because we've got quite a lot of information. So if I give you those information, instead of asking you to find relative atomic mass, I'd like you to find out the relative abundances for Mg25 and Mg26. If all of the information is given there, what we do, try to think of one thing. Is given that the Mg24 has 79%. That means for 26 and 25 all together, you will be only 21% together, or A plus B. So if A plus B equals to 21%, then what is A equals to? A would equals to 21 minus B, right? Make sense? If that one happens, so let's say we always like to use X and Y to do calculations. Let's try to do, if I say I'll let the X be the percentage of mg26, then instead of putting a question mark here, I can do X right here. Then instead of doing X, I don't use Y, because X and Y, you have two unknowns. I think it's not wise to have two unknowns. Try to minimize, as only one unknown in a question would be the best. Then, as this one, if that one become A plus B is 21, or A equals to 21 minus B, and that one would be 21% minus X. Right? Does it make sense? If that is the calculation, that is all the information we've got, then we can put that into a formula. Relative atomic mass is A is equals to the isotopic mass times by the relative atom abundances plus 25. But this one would be a bit tricky because it's 21% minus X. And then we have 26 times X. 26 times X. Then we also need to divide it by 100, right? If that is the case, let's try to complete. Our AM is equals to, is red, I don't like red, try to go back to black. 24.3 is equals to 24 times 79% plus 25 times 21% minus X plus 20X times X divided by 100. So hope you do, when you do year 10 maths, there's something that you know. If this one is a fractions, if you want to bother you too much, you can do one thing, is times it by 100 or times it by the bottom one on both sides to cancel this one. Then 24.3 times 100 equals to 2,730 would equals to 24 times 29. So try to do this again. If we do this again, 24 times by 79 give us 1,896 plus this tricky because this 25 times bracket. So we need to learn that we've learned expanding the bracket. Bracket in back in year 9. So first of all, we need to know we need to have 25 times 21. 25 times 21 is 525. This is plus, so that is end up with plus with that sign. That term is fine. Then the second one is plus 25 times by negative x. We have to turn it into next. 25 times x equals to 25x. Then at the end, plus 26x. Can you see that? If we change this very ugly one into a kind of look a bit nicer now, then we know 2,730 would equals to 1,896 plus 525 minus 26 plus 26 means plus x. And what is x? X can be calculated by doing 2430 take away 1896 take away 525 would be equals to x. Then try to do on here 2430 take away 1896 take away 525. We end up with 9. X is equals to 9. And we try to say this is the percentage of the 26. So therefore, the Mg26, the magnesium 26, equals to the relative abundances would be the relative abundances is equals to 9%. Right? Let's double check with it. 9%, look at the graph. Whoops, supposed to be 11. I've 9% compared with the 11%. What happened? I'm wrong. Maybe that is the problem. So yes, 24.32 may be the problem. If I need to do this like in a very detailed way, then 24.3 is not good enough. So let's try to change all the values a little bit into just 24.32. Then I have to change that one back into 2 here. Then this one is 2,732. And then I have this 32. And I have this one as 32. So let's try to go say this again. I have a feeling that I'm right because the formula can't be wrong there. And yeah, the one that teach us one thing is we have to use more accurate data. So now we have 2432 takes away 1896, takes away 525. I have 11. So that makes sense now. So instead of 9, the relative abundances of Mg26 is 11. And go back to it, and we find that 26 there is 11. So no matter which way, so I can give you the graph and ask you for the relative atomic mass, and I can also give you the relative atomic mass and some information. Then you do need to do the calculation to find out the relative abundances. Okay, so hopefully it works for you and you realize that's not too hard. Maybe we should, maybe you should try to do more question out. So I'll give you more guide questions, like do more questions all about this relative atomic mass and the mass spectrometer. Then I will have one more class later this week, and I will be back. Then yeah, when I'm back, I'm going to check on everything that I sent you. And please make sure you've done them all. Okay, thank you. Bye.